So far, what have we covered? We have, understood, fault models, I guess.
Yeah. Other speakers you have seen, sir?
Uh,
Other
yeah.
speakers, I think I completed the compression of output today, test compression.
Oh, very good.
It has
Very
taken
good.
something
Very
on
good.
the sequential TPG
Very
possibly.
good.
And
So I
Menka,
guess, yeah.
tell us. Menka, आपने क्या कवर किया है? Commercial testing, I think Menka has covered. Sequential testing, Virendra has somewhat covered. Test compression, I just gave an idea in the morning.
Right.
LFSR, somewhat.
Yeah, logic based. Right. So we have covered these topics so far, right? And under sequential test, we have looked at mainly, scan test, right? So today our topic will be memory based.
Yes, sir. Sir. I think memory testing algorithm somewhat Virendra started, but this will be appropriate. Memory this will be, sir.
Oh, okay. He has already covered memory testing, is it?
Only algorithms, elementary. You can go for
Oh, I see.
right. Sir.
Oh, okay, okay. So sorry if it overlaps with whatever he has talked about, right?
I think it is not much overlap. This memory, this will be a new topic.
Mhm. Okay. Mhm. All right. So what is the, in any system on a chip, right? You will have more than one memory, right? So there was a time when, memory used to be off chip, right? And the processor used to, uh, you know, uh, connect with the memory, which is an external memory, right? So today, quite a bit of memory is already on the chip, right? So these are called embedded memories. And the embedded memories, especially in microcontroller based systems, right? Microcontrollers, it is very common to find embedded memories. And there are different kinds of memories. We have non-volatile memories. We have volatile memories. Okay. So what is a non-volatile memory? Uh, it retains its contents even when power is removed. Right? For example, a ROM is an example. A ROM is an example of such a non-volatile memory. Then flash memory is another example. Then there are other technologies like resistive RAMs, right? And then there are ferroelectric memories. So there are many such things, but most I think popular ones are flash memories and ROMs, and there are also PROMs, okay, or electrically programmable read-only memories. Right? So you may have some of those also, a ROM. then flash memory. Volatile memories consist of things like SRAM, right? DRAMs also come under this volatile memory category, but it is not very common to find DRAMs embedded, right? So we do have SRAMs, and there may be many of these. See, it is very common to find a number of such memory modules in the chip because there are usually many processors on the chip, and there may be also accelerators like image processing hardware, right? And to store things like images, you need memory, right? So the summary is a very large portion of the chip consists of memories, right? So it is important to be able to test the memories, right? So let us quickly understand, what memories look like. In particular, let us look at, your SRAM cell. Okay, maybe he has already covered. Professor Virendra Singh may have already covered this, right? So it may be a revision for you. So Vineet, has he already talked about SRAM cell?
I'm not sure. Menka, are you there? I don't think Sir SRAM cell he would have covered. Memory, I think memory algorithms he covered, but
So an SRAM cell is basically two inverters back to back, right? So notice that if you connect two inverters like this, they can be in only two states. So one state is when we have a zero, and the other is when we have a one, right? These are both stable states. And the circuit will remain in the state forever unless you disturb it in some way, right? So we have two, if you look at CMOS inverters, they will look like this. So this is one inverter and this is the other inverter. So the output of uh, the first gate, the first inverter will be connected as the input to the second gate. And similarly, the output of the second inverter will be connected as input to this. And this is our VDD. But how do we write to this cell or how do we read from this cell, right? So for this purpose, so remember that in any SRAM cell, there will be, I'm sorry, in any SRAM memory, there will be a very large number of cells, which are organized usually as a two-dimensional array. So this is an SRAM cell. So there will be a large number of these guys. And the cell, we will have these two guys. These transistors help us select the particular cell, right? So if so, these are usually called bit lines, right? So this is called bit line, and this is sometimes called bit line bar. So they are usually, in an opposite polarity, right? So if you wish to write, let us say, a 1 in this cell, that means this particular output has to be 1, right? So you can make this line 0 and this line 1, right? So that would make this inverter go to the logic 1 state, right? And that will, this state will be reached. And if you make the other way around, right? If you want to make this low, right? You will give a logic 1 here and a logic 0 here, right? And that would send this memory to the other state. And we need to select the cell by activating these transistors. So this is sometimes called the word line. These are connected, right? And that selects the word, entire word. This whole thing is sometimes called the word. Okay. And in each cell, you will have this bit line and bit line bar. Okay. So you have to imagine a whole array of these, right? And there are word lines in all these rows. Okay. So to select a particular cell, we need to provide two addresses. One is called as the row address, and the other is called as the column address. So the way things are organized here, when you select a particular row, all the cells in that row will be sort of red. Among them, we can further go and select the cell from the column address. So it is like that, right? So we can go and select any particular row and any particular column. So if the total address is whatever n bits or something like that, it can be divided into two parts: the row address part and the column address part. And there will be what are called as row decoders, right? So there will be a row decoder which takes this row address and it goes and selects the particular row. And similarly, there will be a column address which goes to the column decoder, and the outputs of the column decoder select the particular column. Okay. And another precaution that we have to take is, see, this bit line, it runs throughout the, imagine a large memory array, right? So this bit line is a pretty long wire, both bit line and bit line bar. And as a result, that will have a large capacitance, right? So if you select a particular cell, see, it needs to be able to charge such a large capacitance, right? It is very difficult, right? This is a one cell. So usually what happens is for reading, okay, I'm referring to reading, right? So if the cell has a 1 here and a 0 here, right? So when you try to read, I expect a 1 to come here and expect to get a 0 here. Right? Imagine this guy was initially 0, okay? Then this one small transistor inverter will have to charge a very large bit line, okay? So to avoid that, they usually do what is called as pre-charging. So they charge this ahead of time, and if this guy is a 0, then it will discharge that particular bit line. If it is a 1, then 1 is already available, so nothing needs to be done, right? So that way they solve the problem of having to wait for a small cell to. It may take a very long time for the cell to charge such a large capacitance. Right? So pre-charging is done in order to avoid that long delay. And the other thing you have to note is even when the even with pre-charging, right? If you are trying to read from a cell, see the difference in the potential between the bit line and this output may be very weak, and it may be difficult to say whether it is a logic 0 or a logic 1, right? The difference between the bit line and bit line bar, has to be sort of quote unquote amplified in order to correctly say whether the output is a 1 or a 0. So as a result, they use what are called as sense amplifiers. Okay, so there are a lot of things inside a memory. So we have the cell array, then row and column decoders. We have sense amplifiers, and we have some additional circuitry for pre-charging the bit lines. Okay, so there are a lot of such circuits inside the memory. Right? What was the question? Somebody raised a hand. Somebody raised a hand. Okay, any questions? Because somebody raised a hand. So if there are no questions, we'll go on. So I don't see anything in the chat. All right. So going back, so what I'm trying to impress upon all of you is that given that there are, the number of cells today, embedded memories, see, this is in megabits. Okay. So as a result, you can imagine that if we wanted to use something like structured faults and so on, okay. See, for example, we could say bit line is stuck at 0, bit line is stuck at 1, and so on. A word line is stuck at 0, word line is stuck at 1. So all those kinds of faults, if you start introducing, the complexity will be too high. Okay, so we usually, don't do this. Okay, so things like stuck at faults, bridge faults. Okay, so these are unthinkable because the complexity of such a test will be too high. So what we do instead is we use what are called as functional fault models. So what is a functional fault, right? The cell, okay, what is its function? It can store a 0 and we can read a 0 from the cell, or we can write a 1 or read a 1. This is all that the cell can do, right? So we can try to formulate a functional fault model by saying there is something wrong with the cell because of which I cannot, it is possibly stuck at 1. The cell may be stuck at 1. So this is a functional fault model. We don't try to go into why that may be the case. Maybe it is because some bit line may be stuck at 1 or whatever. See, we are not going to argue about that. Right? We just look at a functional fault. Similarly, a cell could be stuck at 0. So a good cell will perform like this, right? See, a cell could be in the state 0 or state 1. So when the see, for example, when you power on the cell, there is a 50-50 chance that it will be in state 0 and state 1, right? It will come up in some random state. Now, if I write a 0 in this state, it will remain in the same state. Whereas if I write a 1, it will go into this state. And here, if I write a 1, it will remain in the same state. And if I write a 0, it will come. So this is how a good cell will work. On the other hand, if the cell is faulty, right? So imagine that it is stuck at 0. Then both write 0 and write 1 will unfortunately, send the cell back to this state. So there is no way the cell can go into this state at all. Okay. So this cell state cannot be reached at all. So this is when the cell is stuck at 0. Similarly, the cell may be stuck at 1. Okay. So it may be stuck at 1 in the sense that even if I try to write a 0, it will remain here. So this is a stuck at fault. The cell can also exhibit what is called as a transition fault. What that means is when you power on the circuit or the cell, the entire memory, this cell may come up in either state 0 or state. Okay, the cell, when you initialize the power, it may come up in either of the state, right? Then when you write a 0, it writes the 0 and it remains in the state. When you write a 1, it may go here. But after that, if you try to write a 0, it remains here. Okay. So whether you try to write a 0 or a 1, it remains here. It cannot go back here. So this cell is not really stuck at 0. I'm sorry, stuck at 1. It is not stuck at 1. It can go to state 0, but once, and in fact, it may remain in this state for a long time. See, as long as you don't try to make it 1, suppose during the program, this cell always remained in state 0. Nobody will never ever know that there is a problem with this cell. But if somebody writes a 1 in that cell, then after that you cannot write it. Similarly, I may have the opposite, right? So I may have a situation where I initially it was in state 1 when I powered it on. Then write a 0 will take you here. Write a 1 will keep it here, right? But once it goes there, I cannot get back. So it will always be here. So this is also a transition fault. Again, remember this is a functional model. Okay, how this actually happens, what physical mechanism might cause this behavior is something that we don't want to get into, right? In the same way, we can have what is called as a coupling fault. Imagine that there are two cells. There may be some sort of a coupling going on between the cells. Okay, maybe capacitive coupling or whatever. Okay? Again, we don't know what is the physical mechanism. So because of this coupling fault, it can behave in the following way. I have two cells I and J. If I try to write, something to cell I, okay, J may go to a definite state. For example, it may go to logic 1 state. Okay. So trying to write to I, that means let us say we are causing some sort of a transition. Maybe I is going from 0 to 1 or 1 to 0. Okay. The cell had a 0 and now we are writing a 1, or the cell had a 1 and we are trying to write a 0. This may cause some disturbance in cell J, and it may go to a very specific state, like it will go to state J will become 0. So this is known as an idempotent fault. So some people write it as CFID, coupling fault idempotent. Okay. In the same way, there could be another kind of a fault called as CF invert. Okay. So there, instead of going to a known state like a 0 or a 1, it will toggle. It was already, if it was 0, it will go to 1. If it is 1, it will go to 0. Okay. So this J will toggle. So when I try to do this, J will toggle. Okay. So if this happens, it is an idempotent fault. If this happens, it is called CF invert. So we may have coupling faults between two cells. So given that we have millions of cells, even if you look at only these faults, let us say transition faults, stuck-at faults, and coupling faults, you will see that the numbers are very large, right? if you allow coupling to exist between any two pairs of cells, then approximately 10 to the power 12 faults will be there, isn't it? So that's a very large number of faults to deal with. In reality, of course, all of them are not likely to occur, because what is the chance that two cells which are not physically in the neighborhood will end up with a coupling fault? That may be very low, right? So this you may want to take the physical layout into account and see whether uh, the neighborhood cells will have the coupling or something like that, right? But in reality, people assume that any cell I could have a coupling fault with any cell J. There could be decoder faults. So we may have the row address, and this is my row decoder. Imagine that we are trying to select this particular cell, but there is a structured fault somewhere here, because of which both the rows will get selected. So multiple rows could get selected. Or it could be that no row gets selected. There could be a structured fault on this line, like a structured zero fault. So even though I'm trying to select that particular row, it is not this wire did not become zero. It did not go to one. So it could also happen that no rows got selected, or an incorrect row got selected. These things occur because of some logic faults that may be present in the decoder. And the same is true for columns, right? In the column decoder also, I may face the same issue, right? And there could be sense amplifier faults, right? The output of the sense amplifier may be always one or always zero. And similarly, there is also something called as a neighborhood pattern sensitive faults, NPSF, neighborhood pattern sensitive fault. So if you take a cell in row I and column C, row R and column C, see that cell is possibly surrounded by several other cells. So this is known as a four neighborhood. So there is one neighbor to the west, another to the east and north and south. We can also consider a larger neighborhood like a nine neighborhood, where we also look at these other cells. See, all these cells will have an influence on this particular cell. Okay. We have already talked about the coupling fault. Okay. But in the neighborhood pattern sensitive fault, what could happen is when you write a specific pattern, maybe it is all zero pattern, then maybe this guy also goes to zero. The example is when we write zeros to all neighborhood cells, cell in row RC also becomes zero. Okay. So that could be one kind of a pattern sensitive fault. The other kind could be that when I surround the cell with all zeros, then I cannot make this one. Okay. If it is zero, if it is already one, no problem. Nothing happens, right? But if it is zero, then I can't change it to one. Okay. So I may have, what is called as an active or a passive fault. This is called as an active fault. Whereas I could have a passive neighborhood pattern sensitive fault where when I have a specific pattern in the neighborhood, then that particular cell cannot change state. Okay. So when a specific pattern is written in the neighborhood, then cell RC cannot change state. So these are all, you can imagine how difficult it is to test for a neighborhood pattern sensitive fault. The cell structured faults, I would assume that they are the easiest, right, to test. So we write a zero into a particular cell and then we read it back. If it does not have a zero, if it has a one instead, then obviously the cell is stuck at one. Or at least it behaves like a cell which is stuck at one. Then it could be a cell stuck at zero. We try to write a one and then read it back. We don't get a one, we get a zero instead. So the chance could be that the cell may be stuck at zero. So writing a one and reading it back from each cell and writing a zero and reading it back from each cell, that would take care of cell stuck at faults. In the same way, transition faults are not so difficult, right? So mm, start by writing a zero, right, and then write a one, right, and then read back. Okay, if it does not contain that one, then it may have a transition fault. So it is unable to come back to the original state, right? So it may have a 1 to 0 transition problem or a 0 to 1 transition problem. So we can test for a transition fault by trying to write a sequence. In the same way, if I had to test for a coupling fault, we had to excite that particular fault condition, right? So we had to make sure that if the cell, if we are interested in coupling fault between cell number 55 and cell number 43, then first we had to initialize 43 to some known state, let us say 0, right? And then cell number 55, we had to make it go through a transition. And then again read back what is there in cell 43, right? If it does not contain 0, let us say it has changed state, then we know that there is a coupling fault. So it you may have now realized that it is fairly complex, right? The number of possible faults, right? Even pattern sensitive fault. Look at the complexity, right? The number of patterns that we can have in the neighborhood is very many, right? Imagine if I consider these are 8 neighbors here, and there are 2 to the power 8 patterns that can occur here. If I had to surround every cell with all the 2 to the power 8 patterns, right? The number of patterns that I may end up writing will be huge, right? So people usually, don't use these neighborhoods pattern sensitive faults unless it is there is some evidence to think that this is something that is likely to be there, right? If during diagnosis, if we start realizing that none of the others are there, then we try to look for neighborhood patterns instead of faults. So the most common ones are cell structured faults, transition faults, coupling faults, decoder faults, right? And the last thing is the neighborhood pattern system faults, right? So this is about SRAMs, right? In DRAMs, which are not very common, I think I already mentioned to you that embedded DRAMs are very rare. Okay, people do embed DRAMs, but it's not very common. You may know that static RAM is used for cache memory, right? So DRAM is usually used for main memory. And in microprocessor-based systems, the DRAM is usually external, and we don't embed it inside because the process is very complex. Embedding DRAMs into the SoC is not that easy. So usually people, don't do this, right? So if the DRAM is, if you look at the cell, okay, it may look something like this. So this is a word line, and this is a bit line, and there is only one transistor. Okay. That is the reason why DRAMs, the density is very high compared to SRAM cells, which require like 6 transistors, right? You saw that there are 6 transistors here. Here we have only only one transistor, and that too, it is not like both PMOS and NMOS. Only one kind of transistor is present. So in that sense, also fabrication will be that much less complicated, right? So how does the DRAM remember the logic 1 or logic 0? So we select this word, in order to select this particular cell, we have to put a high here. And if we are trying to, if you put a 1 on this, then you see this guy will conduct, right? And a charge will be stored on this capacitor. As soon as this voltage reaches close to VDD, this transistor will turn off, right? And as a result, there is no path for this capacitor to discharge. Okay? So it will store that one. And next time when we want to read it, again, we do the pre-charging thing, right? If it is already pre-charged, then it will remain in that logic high state if the capacitor here is already charged. Otherwise, it will discharge through this. So that is the way this DRAM cell works, right? But there will be always a scope for some leakage, right? I mean, even though we say that there is a this capacitance is charged, and if this transistor turns off, there is no path for leakage, etc. See, there is always a possibility of leakage in a very slow, but let us say the capacitance has a very high parallel impedance, yeah, parallel resistance. This may be very large, but it can still, cause the capacitance to leak away the charge. So what DRAMs do is they usually DRAMs are refreshed periodically. Okay? So there is a refresh cycle that is constantly done in order to make sure that this capacitance gets charged again. But if the capacitance gets discharged within the refresh cycle, then unfortunately we can't do anything about it. Right? This refresh cycle was calculated. The duration of this refresh cycle is calculated based on the process parameters. but there may be some particular cell where because of a defect it discharges much sooner, right? So then the DRAM will when we try to read a 1, it will actually give us 0. So that is the there is a this particular the fault is also important in DRAMs. Okay, this is a the thing is it is losing its content before we refresh. So any questions so far? Anybody has any questions? Okay. So what we do in memory testing is we agree that it is very difficult to you know consider so many faults and so on. So in the traditional method of testing, right, people have employed what are called as ad hoc tests. Okay. So consider a 4x4 memory. So initially when it is powered on, maybe it is in some unknown state. Okay. So people write, some sort of a known pattern. For example, this is a common pattern called the checkerboard pattern. Right? So we write so this is known as a checkerboard pattern. So an algorithm will be created, right, which will go from this cell, okay, row by row and column by column, and we'll figure out what to write. Okay, so this is the checkerboard pattern, and then we will read everything back. We will read back the values that are written, and alternately we expect a 0 to be read and a 1 to be read, etc. Okay, and if there is any uh, suppose there is some cell where we were expecting a 0 and actually we got a 1, then we record that error. We say that at this particular row and at this particular column there was an error. Okay, so this is the checkerboard pattern, and it may be after doing this we may do the reverse. That means oops, we may go and reverse all the bits. Okay, so this will make sure that structured faults, etc., will be properly covered. So the see in the there is a built-in CPU, right? Remember that I told you that in our system on a chip, right? There will be typically more than one CPU, right? There may be multiple microprocessors or microcontrollers and so on, right? So this activity of testing the memory can be done by the embedded CPU also. Okay. So there we have to assume that already the CPU has been tested, and as a result, we can trust that the CPU will write this particular pattern, read it back, and note down wherever there is a discrepancy and all that, right? So if you do that, it is known as CPU BIST. Okay, so that is called a CPU BIST. That is not, uh, you know, if you don't want to do CPU BIST, then you have to put what is called as a memory BIST controller. So the BIST controller will need some logic in order to generate the row and column addresses, right? It may need counters to, there may be a row counter which goes from 0 to 3, and there is a column counter which goes from 0 to 3, right? And it will generate the addresses systematically 0001, 0203, 1011, 1213, etc. And it also knows what to do. That means initially we are doing the write. So it will send write pulses. See, remember, in order to write to the cell, we need a write signal, right? And also the data. So somebody has to generate the address, the control signal, and the data. So that will be done by the BIST controller. And then in the next phase, it will read everything back. Okay. So that also is a logic that the BIST controller needs to have. And it needs a comparator in order to see whether the value being read is the same as the value being expected. And if there is a discrepancy, it has to note down the particular row and column. Right? And then it has to move to this second phase where it'll write the other sequence. So the BIST controller will have, it is almost like a small, it cannot do much else, but it is a special purpose engine which can only generate these row addresses, column addresses, write and read control signals, and the data comparison. So this is what the BIST control is intended for. Right? That is what is the content of the BIST control. Okay, this is the memory BIST control. There may be many other patterns. So pattern people have also tried other patterns. For example, you can try what is called as row bars. And you can also try what are called as column bars. So this is the checkerboard pattern. These are the row and column bars. So you can also imagine another kind of row bar pattern where all these are zeros, all these are ones, all these are zeros, all these are ones. So again, the BIST controller may be capable of generating this pattern also. Okay. So usually the CPU, I'm sorry, memory BIST controller is capable of applying more than one algorithm because it depends on the the size of the memory. It depends on the DFT engineer who engineered that memory-based controller. That person may have felt the need for running these additional patterns. So there may be opportunity to run more than one kind of a pattern. Okay. There is also the solid zero pattern. Okay. You can imagine what it is. Solid zero. That means all the cells are zero, and solid one patterns. Then there is also what is known as the parity pattern. What that does is it looks at the row and column address. Suppose the row address is 001 and the column address is 011. So count the number of ones. Okay. So in this case, the number of ones is 3. Okay. And if you are looking at even parity, you will write 1. So write 1 in cell 1 comma 3. Okay. So this is a cell 1 comma 3, row 1 and column 3. If you are doing even parity. So this is also another pattern. So when you may have noticed that when you boot your computer, typically the memory gets tested, right? And the time it takes to test the memory depends on the size of the memory. See, nowadays CPU, I'm sorry, your laptops, they contain a lot of cache, right? And a lot of main memory, right? I think it is not uncommon to find, even gigabytes, right? Which was unheard of at one time, right? So imagine, testing such a large memory using patterns like this. So you will realize that even if I do this simple checkerboard pattern, I will have to write, to all the bits, right? I will have to write to every cell at least twice, and I have to read back from every cell at least twice. Okay? So even the checkerboard pattern will require 4n operations. So any algorithm that takes a linear amount of time in terms of the number of bits is considered okay, right? Because I don't know whether we can do anything better than that, right? So this is acceptable, right? There are which are more complex. See, you may have realized by now that these patterns may not uncover so many faults. See, all of them, because we are writing both a 0 and 1, stuck at faults are easy to detect. Maybe some coupling faults can be uncovered because what is going to happen is, see, I wrote a 0 in this cell and then I wrote a 1 in this cell. Okay, so I have caused this cell to go from 0 to 1. And if that causes this to flip, right, then we will have caught that problem. So we may be able to find some transition delay faults, some coupling faults, Okay, but there is no guarantee that all of the coupling faults and all the transition faults will be detected. Okay. Many of them may go undetected. The same is true here. See, if there is a coupling fault between these two, that is not even getting activated because both of them are one. Okay. Maybe if we do both row bar and column bar, there is a chance that we are allowing that coupling fault to get activated. Right. So these ad hoc patterns that people have created, you know, they are known to be okay. I mean, not they may not detect all the faults, right? And frankly speaking, detecting all the faults is, very hard because it will take too long. So we must accept that we will not be able to uncover every fault there is. If you look at all the faults that I mentioned earlier, right? Cell circuit, row decoder faults, and coupling faults, neighborhood pattern sensitive faults, etc. So we must be convincing ourselves that we can't do all of that because it will take too long. So people have tried other patterns, okay, like galloping patterns and the so here is one more pattern. So imagine that initially the cells have some unknown values. So the galloping pattern will initialize all of them to zero first. Okay, all these will be zero. So that is a solid zero pattern. Then write a one here. So we have brought in a one, and after that all the values will be read. You understand? So it's very expensive. This will take n writes. Okay, we have written to all the cells. N is the number of cells. So we have performed n writes. Okay. Here we perform one write followed by n reads. So you can realize that it's a good test in that sense because when I write a one here, any one of these could be disturbed and they could become one because of the coupling. Now, because I'm going to read all of them, in a way, I'm catching a lot of coupling faults here, right? And then it will, then it will go back and, make this zero again and move the one here, okay? And then again, all the faults will be, all the cells will read. So we are doing n reads here and then n reads here, and that will be done everywhere. So this is known as a galloping one. Okay, the one is like, it's called as one is supposed to gallop. So you can see that there will be n square read operations and n write operations. And if that is not going to be enough, you can also have a solid ones pattern, right? So we can also do a solid one. Okay. So start with all ones here. So let me just write it. So this is the galloping one. So here we took n writes. Here one write plus n reads. Then one write plus n reads. And so on. Okay. So totally we would have done n plus n writes plus n writes again plus n square writes. So this is very expensive. So if n is in millions, you can see that this will become 10 to the power 12. So instead, one could do what is called a marching test. So in a marching test, again we'll start with maybe the all zero pattern. Then we'll bring in a 1. Okay. And then we'll bring in a 1. Okay. And similarly, we'll bring in a 1. I think somebody asked a question. Let me see if the chat is. N Naga Vijaya Lakshmi. In first grid, why not it be N reads? Sir? See, we after initializing the here we are only writing. We don't read. We write all zeros, right? We don't want to read all this. We write all the zeros and then we bring in a 1. Then we want to make sure that everything else is a 0. Is that okay? Sai Kumar. In coupling fault, one cell will couple with nearby cells, right? Then, yeah. I mean, that's right. I mean, coupling faults. But see, the point is that we don't know what is that neighborhood, right? Only the layout will know, right? In our picture, it may appear that this cell is neighbor to this. But when you do the layout, it may not be like that. Okay, so it is difficult to find physically which ones are neighbors unless we know the layout. Okay, so that is the reason why when we are talking about this coupling faults, etc., it is difficult to take physical layout into account and things like that. But if we have that information, definitely that should be used in order to reduce the complexity of the coupling faults. I hope the answer is so everybody understood what is happening in marching tests. Okay. This is 0. So here the 1 is supposed to be marching. So initially all were 0. Then we bring in a 1. Then we don't erase this. we bring in the next one, and so on. So slowly, all of them will get filled with ones. So let me show you the notation for marching tests. So marching tests are what is really used. Okay, people may not use all these galloping patterns, etc., because they are too complex. But marching tests are the ones which are really used, right? So there is a Professor Van de Gore, right, who introduced a particular notation. Professor Van de Gore. So he introduced a notation which says this means in the increasing order of cells, cell addresses. So if you number the cells 0, 1, 2, 3, 4, 5, 6, 7, etc., etc., then this increasing order means we are going in this increasing order of cell addresses. So 0 to maybe 15. Similarly, 15 down to 0 will be written the other way around. So uh, this means in the increasing order of cell addresses. Whereas this means in the decreasing order. And sometimes they also say if you write like this, it means it doesn't matter which order, any order. So if I write something like this means write 0 into all the cells in some order. So W0 means write 0. W1 means write 1. Read 0 means read expecting a 0. If it is not 0, I mean, read and compare and see whether it is 0. If it is not, then we have to note it down that there is a fault. Similarly, read 1 means some people simply say read 1. We don't have to write read expecting a 0. We can just say read 0. So here the first step that we did was we write all zeros. Then maybe we are in the increasing order, we may write a 1, okay, followed by, I'm sorry, read 0 followed by 8. Read 0 followed by 8. My apologies. Sorry. So what it means is, after writing all the zeros, I go to this cell and I see whether it is still 0. If it is not, then there is a stuck at 0 fault, right? Then I write a 1. Okay. So that will cause a 0 to 1 transition on this particular die, right? And it may disturb some of these cells because of coupling, right? So I'll now go to the next cell and I'll again see whether it is still a 0. It may be now it may have become 1 because maybe the cell has a stuck at 1 fault, or maybe there's a coupling between these two guys. Okay, there is a CFID or a CF inverter fault between these two guys. Okay, so I will read all the cells and see whether there is a 0. Then I'll write a 1. So at the end, all of them will have 1s. I will reach a state where all the cells are 1s. Right? Then I can continue. And in maybe in some other order, I can read a 1 and try to see. So March tests are of this form. So you should understand this notation. Mhm. And some March tests which people have used. Here is one. So the first one, I think in the early days, Professor Brewer and Friedman proposed something like this, right? Then Van de Goor proposed this in the 91, right? So this is what I think. No, I didn't write this one. This is called MATS plus plus. So in some order, write all zeros. In the increasing order, read a 0 and then write a 1. And in the decreasing order, whatever one you had written, you try to read it. Then write a 0 and then read it back. So this is known as the MATS plus plus algorithm. Right? Like this, you will find many algorithms. So let me see if I can find more such. You will find all these good stuff in Professor Vishwani Agarwal's book also, and the slides are available here. Yes. We can maybe look at this guy. So these are slides that Professor Vishwani Agarwal has prepared for the book that he has authored, right? And, so here he also shows that how the size of the number of the memories has increased. Okay, it has gone from megabits to there may be even some gigabits of memory in some chips, right? And if you are going to use an n linear algorithm to test, right, then the number of seconds it takes to test that kind of memory, even if it's a linear algorithm, you can see it takes about 128 seconds, okay, which is about little over 2 minutes. But if you are going to use a n square algorithm here, then this will take a humongous amount of time, right? So even if it is 1 megabit, you will see that it takes like 18 hours or something. So we cannot afford to use. Here you will find detailed explanation. Here it is. This is what I want. Right? So we can see MATS plus plus we just saw. Right? This is Professor Van de Koer's proposed algorithm. Then there is a March X, right? And there is a March C minus, right? They all have the same, general organization, right? In the either increasing or decreasing order, write 0, then read the 0 back, write 1. In the decreasing order, read 1, then write 0, then in the increasing order. So the amount of time this will take will be 1, 2, 3, 4. 4 times n. 4n is the complexity of maths. Here it will be 5n. Here it will be 3 plus 2, 5 plus 1, 6, 7. So possibly he has ordered all of them in the increasing order of test time. Okay. But the more time you are willing to spend, the more faults you are likely to catch. So uh, the number of different faults that there are, right? A very simple algorithm like maths may not catch quite a few faults, right? It will catch all the structured faults, right? It may catch, I think, transition faults may also be caught. It may not be, may not be. We have to argue. We have to spend some time arguing whether transition faults are caught or not caught. What about row decoder faults, right? So the analysis of each of these algorithms will be given in the paper where we propose these algorithms, right? So you may want to look at least one or two of these. Okay. So there is a theorem, right? If in one cycle, right, in the increasing order, if you put read x and write x bar, if you see this in any marking algorithm, and in the decreasing order, if you see read x bar and write x, right? So if these two conditions are satisfied, right, then it will catch, the address decoder faults. So this is a theorem that is given in that book, right? And here you can see the analysis of these algorithms, right? All of them generally catch stuck at faults, right? Whereas maths, you can see it doesn't even catch all the transition faults, right? But more expensive algorithms tend to catch all the transition faults, right? So this is these are the complexities. We already saw that, right? So today, I think some of the popular algorithms that are used are March Y, March C minus, right? So these are all used. And like I mentioned earlier, the best controller must be capable of applying more than one algorithm, right? So your best controller, the memory-based architecture may look somewhat like this. See, if there is a memory, typically it requires an address bus, it requires a data bus, right? Write bus, write data, read data, and maybe some control bus. Right? So normally it is the CPU which produces these addresses and write data, etc. What we could do is we could have a multiplexer here. So this is coming from the CPU, but we can have a memory-based controller. So in the test mode, the memory based controller will produce the addresses for the memory. Right. Similarly, it will produce the data for the memory, and it will receive the data being read. And here also it may have a mux here. Hmm. So this is your memory. So the BIS controller will implement that algorithm, the marching algorithm of your choice, right? And like I said, it should be programmable. Okay, it should be programmable to handle more than one algorithm. So usually it is the March algorithms. Right? Hmm. And inside the BIS controller, it will have a it will have a comparator to compare the value being read from the memory with the expected value. And if the comparator produces an error, meaning the values are not matching, then the BIS controller will have a sort of a internal buffer where it can note down all these failing rows and columns. So there may be room for a certain number of such entries. Okay, if it exceeds this number, then maybe that memory, we need not use it at all. So, like I mentioned, memories will invariably have faults, and depending on the application, we may be even able to tolerate that error. Okay, the error may be tolerable error. We don't throw away the. See, in logic, if you find a fault, then you can't use that, right? It is not usable. But in memory, if let us say a cell is stuck at zero or something like that, right? Imagine that that memory represents some image. Okay, it is storing some image, and some few cells are stuck at zero or stuck at one. It may not make a big difference, right? So we may it's application dependent. Okay, we may find that it is okay, it's acceptable. But if it is the application is not image processing, maybe it is something else where this maybe it is some finance calculations or something like that, right? There even a one bit error may be a very significant error. We don't want such errors, right? So the rejection is based totally on the application. Right? So when errors are detected, they will note down these row and columns where the errors are, right? So one thing is to tolerate the error, the other may be to repair that error in some way, right? So what could be done is instead of having a fixed number of rows and columns, you may build in a few extra rows and columns. So these are your spare columns and these are your spare rows. So once we know where the errors are, so maybe it is an error here and another error here, another error here, another error here, here. And we may have, let us say, two rows and two columns. So we may have two extra rows and we may have two extra columns. So now the controller can decide using some sort of a optimization algorithm. These two may be in the same column, and it will say, look, I'm going to whenever the memory is given a this column address, right? Let us say this column is 49. Okay. Then instead of 49, go to 1027 or something. So it will be internally mapped to this. Similarly, these two may be in the same row. So this row may be, let us say, 95. And there may be one thing here which is 1405. So this guy will be mapped to this. So this is called as built-in self-repair. So during the process of testing, the faults are identified, and you will have to have some additional logic for the memory to redirect these faulty rows and columns to the good rows and good columns, right? And that way your yield will improve. See, if you have to, if you end up throwing all the chips because there are some faults in the memories, then there will be no yield at all. All the memories will definitely have faults. And you can use things like, okay, this error is tolerable. We don't have to worry about these errors. Because in signal processing, one or two bits here and there, it may not really matter. But if it is something more complex, maybe it is some finance application or something like that, then even one error may not be tolerable. And the best logic is embedded into the chip, so there is an extra area overhead, right? So BIST will cost you in terms of area. So we need all this BIST controller, these multiplexers, all the wires that have to go around, right? And another see, what if there are many memories, right? See, that is a big problem. I told you, right, in the very beginning, I told you that there may be many memories in the same chip. So I may have a, some sort of a cache memory here, right? And there may be multiple caches, data cache, program cache, and then there could be, scratchpad memory, right? There could be image memory, and so on. Okay. So it is not uncommon to find hundreds of memories. Now the DFT architect will have to decide how many memory-based controllers will be required to test all of these, right? See, if you bring in too many memory-based controllers, then area will go up very significantly, right? And the complexity of the implementation goes up very significantly. Right? So often people may gravitate towards a single memory-based solution. Uh, so you need a programmable list, okay? Because these caches may be of different sizes, the image memory may be of a different size, etc. So then, you will have to think of creating a programmable list, right? And different algorithms may be required in different cases. See, they may not apply the same March algorithm for everything, right? in the image processing example, maybe we are willing to offer a slightly less time consuming because it's a very large memory, right? We may have maybe 256 by 256 pixels, and each pixel may have red, blue, and green, right? So it's a very large memory, and bit errors may not be such a big deal there. So we may be willing to use a less time consuming algorithm. Whereas maybe for cache, etc., we may use a different algorithm. So the this controller should be programmable, and that is programmed by the DFT engineer, right? Plus, even the algorithm that is required for assigning spares to the faulty memories, even that is controlled by the DFT team. And if I put a PBIST somewhere here, you can imagine the complexity of routing these wires, right? These addresses are very large. Maybe it is a 32-bit address and maybe 32-bit data. So these big buses will have to be routed all over, right? So the complexity of memory this lies in not only the essential concept is not such a big thing, we can understand these things, but the real hard part is, how do you, sort of where do you place these cells and I'm sorry, where do you place these controllers and how do you, connect all these things and make sure that they're all connected properly, right? And make sure that they don't upset the timing of the chip. So that is the real hard part. So you know, memory based impacts the physical design, right? So all the performance, right? We'll have to make sure that we work closely with the physical design engineers to make sure that the timing is not impacted. So that is the challenge in memory based, right? Then there are other things that people are doing. For, uh, may be possible for you to build some error ECC memories. So these are error correcting memories, or they use error correcting codes. ECC stands for error correcting codes. So typically they are based on this parity. And you may have done this in your maybe some other class, like computer architecture or something like that, or maybe in communication or something like that. So this is the same thing. So for example, Hamming codes. So Hamming codes are very popular. So see if something about Hamming codes, something readily available. Hmm. So the idea here would be that see if you have about this? This is so imagine that the data is 4 bits. Okay, so we have a 4-bit data. We want to store a 4-bit data in the memory, right? And we want to be able to specify where the error is, right? The error checking code or the error correcting code should be able to detect and correct a certain number of errors. So we look at a single error correction. So SCC means single error correction. So the way it works is we add a few extra bits. So let us say there are n bits in the data, and we added the p parity bits. So what is a parity bit? You may remember this from your computer architecture or something like that. So if I have this data, right now the number of ones is odd, right? So we can add an extra bit called as a parity bit, which reflects the fact that the number of ones here is odd. So if you are using even parity, you will add another one here. This is an extra bit called the parity bit, so that the number of ones now becomes even. Okay. So another example is 0110. See here the number of ones is already even, so we'll add a 0. So the parity bit is calculated based on the number of ones which are there in the data. So here instead of one bit, we are adding multiple bits. We're adding multiple bits. And what we do is when the parity bits are finally assembled, okay, they may spell out and say that this is 011. So it should be able to say that in the third position there is an error. If it says 000, that means there is no error. If it says 100, that means the fourth position has an error. Okay. So the number of parity bits that we need, right, should be able to find a single error in any one of these positions. Okay. So parity bits can be in any of the 2 to the power p, combinations. So this should be at least equal to n plus p. So for example, if n is 4, we have to try which one will work. So 2 will not work. Okay, if you try 2 parity bits, right hand side has 6, the left hand side has 4. So this will not work. But if you try p equal to 3, it will work. So this is 8 and this is more than 7. So that is why for 4 bits, we will need 3 parity bits. Okay. Of data, you will need 3 parity bits. So together, So let us label these as 1 to 7. The parity bits are placed, uh, in positions like 2 power 0, 2 power 1, 2 power 2, etc. So this will be a place where the parity bit 1 is placed. This will be the place where parity 2 is placed. And this is the place where the parity 3 is placed. The data will occupy the remaining positions. So if this is D1, this will be D2, this will be D3, and this will be D4. So this is the so-called Hamming code, right? Now, how do you calculate P1? P1 is the parity of all the bits which have a 1 in the 0th position. See, this is, we chose P1 to be in the 2 power 0 position. So P1 is a parity of all the, odd ones. So D1 XORed with, then the next one will be 5, which is D2 and D4. So these are the odd ones. Okay. 2 power 0 means the least significant bit position. Wherever that is 1, we take those. P2 is wherever the second position, that is a 2 power 1, right? So if that is 1, we use that one. So 0 1 0 is you know uh, 0 1 1 is D3, D1. Okay. So write it down: 0 0 0 0 1 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 and 1 1. So we in for P1 we chose wherever this was 1. Okay. So we chose 3 because that's a data bit. Okay. Then we chose 5, which is a data bit, right? And 7. For the second one, we choose 3 again because this is a 1, right? So that is D1, and then you choose 6, which is D3, and we choose D4, which is a D7. And similarly, last one will be P3. So wherever it is 1, like 5, 6, and 7. Okay, 5 is D2, and 6 is D3, and 7 is D4. Okay. So let me repeat. We chose the parity bits in positions 1, 2, and 4. Okay, which are of the form 2 power n. And P1, which is this first parity bit, is the XOR of, or the parity of, all the bits which have a 1 in this position, in the least significant position, and similarly 1 in uh, the position 1, and 1 in the position 2. So if I give you some data, for example, the data could be 1 1 0 0. Okay. I'm sorry, 1 0 1 0. I took 1 0 1 0. Then P1 will be XORed of D1, D2, and D4. So D1 is 0, D2 is 1, and D4 is 1. So this will be 0. Then P2 is D1, D3, and D4. So D1, D3, and D4. Okay, so it will be 1, right? And D2, D3, D4 is all 1, 0, 1. So this will be 0. So in the memory, instead of storing the data, if you only store the data, we would have needed 4 bits. We will also store the 3 additional parity bits. So it will take us much more memory, right? For every data of 4 bits, we are choosing to store 3 bits. Okay, so it comes at the cost of a significant amount of area. Now, how does this work? See, suppose something goes wrong and we end up, reading 1100, etc. Suppose 11100010 is read. Okay, so something went wrong and we read a 1. It may be a stuck at fault or something like that. So we recompute P1, P2, P3. Okay. So what is the P1 here? The new values of P1. So this is our D4, D3, D2, P3, D1, P2, and P1. Right? Now P1 prime for the possibly erroneous data is D1, D2, D4 XOR. So D1 is 0, D2 is 1, and D4 is 1. So 1, 1, and 0. So P1, 3 will be 0. So maybe I should have written this in a color. So this is what is computed. Similarly, P2 is D1, D3, D4. This is D1, this is D3 and D4. So that is also 0. Right? And P3 will be D2, D3, D4. So D2, D3, D4 is 1. Okay. So that will be calculated as 1. Okay. So the original parity was 0, 1, 0. Okay. So the original parity was 0, 1, 0. But now we are reading 1, 0, 0. So if you XOR these guys, we will get 1, 1, 0. Okay. So that is pointing to sixth guy. Okay. And it is pointing out that the error is here. So which is what was the case, right? I had changed this to 0, from 0 to 1. So what is the essential idea? We will if the data is, let us say, n bits, okay, so try n equal to 32. So 2 to the power p should be greater than or equal to 32 plus p. So 6 might work, right? 5 will not work, 6 will work. So p equal to 6 will work. On the left hand side, we'll have 64, and on the right hand side, we'll have 37, right? So for 32 bits of data, we'll have additional, parity bits, which are 6 bits. So we'll have P1, P2, P3, P4, P5, P6. So they will be positioned in all these. This will be at position 1, 2, 4, 8, 16, and 32. and the remaining 32 bits will be meant for data. And we will need XOR trees to calculate P1 to P6. And when we retrieve the data, we again will recompute the your parity bits, okay, P1 prime to P6 prime. And then if you XOR these guys, okay, whatever we computed now and whatever we retrieved, if it says 0, 0, 0, that means there is no error. If everything is 0, there is no error. Okay, that means the original parity is the same as the new parity. That means nothing has to be done. Okay? But if there is a difference between the parities, then it will point to one of these guys and say that there is an error. So we are spending extra in terms of the number of bits that we are storing plus this XOR tree. Okay, that is also going to cost you a lot of money, right? So area-wise, ECC memories are expensive, but when the application demands, right, they will go and implement ECC memories. It is mandatory nowadays for applications like self-driven cars and things like that. There, as you may know, nowadays cars do a lot of things, right? Driving and maybe reversing, for help to the driver for reversing and so on and so on. So errors may be very expensive, right? Having an error in the memory may cause wrong calculations and things of that nature, right? So we cannot afford to do that. As a result, they demand that ECC memory should be used. Okay. And the second thing is that in these applications like cars and so on, they also insist on logic based, right? We talked about logic based in the last class. So logic based is necessary because the chip may have to be tested multiple times. So the chip's lifetime is very long. So once you buy an expensive car, you may use it for many years. So during the period of usage, the chips may have to be tested uh, periodically, right? That will be possible only if there is a logic test on board, right? I think we have possibly run out of time. I have exceeded the time by 4, but if any questions, I'll be happy to take. Let me see if there is any chat. Okay, somebody has asked Sai Kumar. That is an old one. There are no questions, looks like. Any questions about memory test algorithms and how match tests are the ones which actually make sense from a runtime point of view? Okay. So as a practical exercise, maybe you can try. Um, I will try to give an exercise. Try to give an exercise that you can try. Any questions? If transistor not working properly, then how we detect faults? Mm, if transistor not working, what does it mean, Professor? Which transistor are you referring to? So transistor means which transistor? Are you saying if the memory bit itself has a fault, then how do we detect? I don't know what the question is. See, that is a classic problem everywhere, right? It is not only for memory based, it is true for logic based, it is true for scan test, everything, right? See, if the test equipment itself has a fault, then obviously, the testing will fail, right? So usually the memory based controller will have to be first tested, right? So the memory based controllers will have a lot of flip flops and things like that. So they are also part of the scan chain, right? So we will first go ahead and check whether the memory based controller itself is fault free. If that is what you are asking. The same is true for logic based. Is that the question that you were asking? Some wiring or physical layer shorts in transistor. See, those are anyway. I think I may have mentioned to you about defects and faults, right? So those they will all manifest themselves in some fault only. See, if the wire is open, it may act like a stuck at zero fault, right? If in CMOS, an open wire will typically act as a stuck at zero fault, right? So similarly, other physical faults or defects will be modeled as either a stuck at fault or a bridge fault or it may become a transition delay fault. See, we cannot talk about physical defects. That is what I'm trying to say. I hope you understand that defects are, it's very difficult to talk about defects. In the memories also, see, we only talked about faults. In that too, we talked about very abstract faults like cell stuck at zero, coupling faults, things like that. Why does the coupling fault occur? Right? I have no idea. Why will that cell behave like that? Right? They may have developed this fault model based on some experience, right? And it is very difficult to understand why that defect arises in the first place. I'm sorry, why that fault arises in the first place and what defect causes that, right? It is difficult to say. So we don't even think about talking about defects, right? Because we are not interested in going into what is the reason why it is doing like that, etc. We don't worry about that. Okay. Any other questions? Okay, then I'll see you tomorrow. Okay, thanks. Bye bye.